Okay, welcome everybody to NYADI.edu, the College of Transportation Technology. And this is for my evening class, Diesel Accessories. So the first lecture that I'm going to be doing for you guys is going to be talking about turbos, okay, and what that means and for, for the diesel engines, okay? Now, the biggest difference between a diesel and an automotive or automotive or car engine is the way that the fuel is basically ignited. So, one has spark plug, which is a spark ignition, and the other one is compression ignition. So what does that mean? Well, that means that the compression in a diesel engine is so high that any kind of fuel that you spray into it will basically ignite. And that's why they use, diesel engines use a very, very high compression ratio. Now, one of the things that these diesel engines are going to need in order for them to produce any kind of power is going to be a turbo, right? And this first part of the lecture, we're going to be talking and discussing turbochargers. So, first thing, what is a turbo? Okay, how does a turbo work? Well, let's draw it over here for a second. Let's see what we got. All right, so we're going to draw an engine. All right, so here's the cylinder head, and then here's the exhaust. And basically, what we want to do is, let's say the air going into an engine can only reach close to the speed of sound, which is about 700 miles per hour. So when the pistons are going down, okay, in the intake stroke, they're basically pulling, all right, air through the intake valve at a close velocity, to the speed of sound. Obviously, it can't break the sound barrier, okay? So we're limited to that. The restrictions in the air intake systems and all these other things have an effect on how much air we can actually put into the cylinder, which is basically called volumetric efficiency. So this is the amount of air that we can actually put into any cylinder, all right, with the naturally aspirated, which means that with no turbochargers, no superchargers, no forced induction system. So we call that volumetric efficiency for naturally aspirated engines. All right, so in the engine or a diesel engine, since we don't have any form of spark plug, we have to make sure that when the piston comes up, the compression area, the squench area right here, has to be, well, as the piston comes up and the compression ratio goes up, the temperature inside this area, this volume of area, when the piston is all the way to top dead center, there's a little area right there, okay? And the compression ratio is basically how much volume this area is, and when the piston goes all the way down, right, let's say, we have a little volume like this, okay? And this is 1 cc. So the engine or the piston goes down 10 cc's, okay? And so when a piston comes up and fills this 1 cc area, since it went down 10 cc, we call that a 10-to-1 compression ratio. Okay? Now in the diesels, we're talking about 22, 16, 18, things of that nature on up. And what changes the compression even more is when we start putting the turbo onto it that brings the temperature up, and we're going to get to that in a minute. So, volumetric efficiency. Naturally aspirated, we can only fill the cylinder up, let's say 70%. All right? On a vehicle, let's take an automotive car, okay, first of all. And let's talk about making power first. So, the perfect air-fuel ratio, okay, for a car, right, and a gasoline engine is going to be 14-to-1, okay, as far as 14 parts of air, 1 part of fuel. Now, they measure it in pounds, okay, by weight and stuff like that, but, it's a little bit more confusing. So I like to use 14 parts of air to 1 part of fuel is a much better scenario for you guys to think about. Okay, this is the perfect air-fuel ratio. So below this, 13-to-1, we call that the engine is running rich. Okay, above this 14-to-1, this is lean. Lean also means hot. Okay, rich will be colder. All right, so keep that in mind. Now, this is the perfect air-fuel ratio. We filled up the cylinder 70%. So one of the first things that you guys need to know about making power and horsepower is how we can fill this cylinder up more. Okay, let's say you guys put a cold induction intake into your car. That's one of the first things that most students or most people actually buy. It is basically pulling colder, denser air that contains more oxygen. Okay, so if it contains more oxygen, we can put a little bit more fuel. All right, and we basically are going to make a little bit more power. So we put a cold intake system in. And let's say because we have a higher density of oxygen coming in, the computer automatically picks this up, sprays a little bit of more fuel in it. And let's say now that the volumetric efficiency, okay, goes up a little bit, right? Because not only that, we've reduced the restriction in the air system. Here's a K&N air filter, right? Something shaped like this, which reduces the restriction. So when the intake valve opens, more air can rush in, and especially if it's picking up from the colder part of the engine. A lot of them are mounted in the bottom side, right? Cooler or above, someplace in the fender where it's out of the engine or combustion area, okay? For that purpose, to pick up a little bit more denser air in that area. But the biggest part of it is it has less restriction. So less restriction means that we can fill the cylinder up a little bit more. Now we used to have it stock at 70. We put a cold air, okay, intake. All right, and now we can fill it up to 72%. Now, 72% volumetric efficiency is a little bit more. That's why most, performance enthusiasts get a little bit more power. Not much, hey, but anything is better than nothing, right? We didn't have to add anything else except an intake, so everything is, you're getting a little bit more power, even if it's 5 horsepower. It all depends. 5 horsepower is better than no horsepower, right? Okay, so we have a cold air intake. We're increasing the volumetric efficiency. Now, here's another thing that we can do to increase volumetric efficiency. Let's say I have a little 4-cylinder, and I want to get more power out of my engine. Okay, so again, we're talking naturally aspirated. So let's say now, what can we do? So now we go into camshafts. So now the camshaft profile changes, which has lift and duration. And so for all purposes, we're going to get back into making performance and stuff like that because I want to get the turbochargers, and I'll go into more in-depth with cam profiles. But let's say that the valve allows more air on the intake stroke to fill the cylinder up a little bit more. So now let's say we put a new cam in there, okay, and now we're filling the cylinder up to here, right? Then we also ported the cylinder head, all right, and we also have the exhaust ported. So the maximum that we can get naturally aspirated, all right, let's say it was regularly stocked 70%, and let's say now we're going to be somewhere like you guys did a good job, all right, you ported 3-stage port job, all right, really good, let's say exhaust port, and you guys also have a tuned exhaust. Again, we're going to get to that later. And let's say we got now 78% volumetric efficiency. So now we're up here with 14-to-1 air-fuel ratio. This is why when you guys are increasing the camshaft, when you guys are putting cold air intake, this is why you guys are getting a performance gain. Now, here's where we're going to get into another part of making power, which is called thermal efficiency. Okay? Is it still recording? Okay, thermal efficiency. Now, what does that mean? Well, let's say I have 2 identical engines, 2 complete identical engines side by side. All right? And the difference is one engine has, let's say 8-to-1. 8-to-1 compression. And the other engine has, let's say, 9.5. Okay? Now, why does this one make more power than this one here? Because that engine is going to make, side by side comparing, same camshaft, same displacement, same everything. The only difference is this has a static compression of 9.5-to-1 versus 8-to-1 compression. Why does this one make more power? Why, when you buy into drag strips, why when you guys are racing or you guys are building a race car, you guys are now running, higher compression engines, naturally aspirated, because you're not in the turbos or superchargers. You got to run naturally aspirated. So you're going to run as highest compression as you can get away with. Why is this 9.5 going to make more power than 8-to-1? Has to do with something called thermal efficiency. Okay? And what thermal efficiency means, just because we filled the cylinder up 70%, okay, doesn't mean that we burned all the fuel 100%. So out of the 70% that we filled up the cylinder, let's say maximum we only burned 80% of it, okay, to use to expand and actually drive the piston down. This is thermal efficiency, okay, how well we're actually burning the fuel. One thing is getting the air-fuel ratio in. Another one is how much of it do we actually burn, okay, to actually do work, right, to push the car down the road. So thermal efficiency. So now let's look at it this way. Let's say if you guys take an injector and you spray fuel into an oven and you spray fuel into a freezer, which one of the two is going to burn the fuel more efficiently? The one in the oven is going to burn more efficiently. Okay? So what happens to the compression ratio if it's higher than this one? The internal temperatures of the engines is actually higher. So the more compression you have, when the piston comes all the way up in a compression stroke, that little squench area that I was talking about, in here, in this little area, okay, when the piston reaches top dead center, this little squench area right there, okay, this has a certain temperature that's related to the compression ratio. Let's say with 8-to-1, let's make it, for numbers purposes, 100 degrees. Okay? And now the engine runs 100 degrees. So now 9.5-to-1. Let's say it's 175 degrees inside this area. Now you guys can see the difference between using a freezer and then using an oven. That's the difference. So we got a little bit more heat in here to help the fuel burn. Okay? Because that's what we're talking about as far as thermal efficiency. How efficient, right, is the engine actually burning the fuel that we're actually putting into, all right, our engine? So now